Good afternoon. So this is a post-lunch session, which is a bit difficult. Yeah, let's see. So I am Charu. I am a faculty at Machine Learning Lab at IIT Hyderabad. Right? And I think, mention maybe in the next slide what I work on, what I have worked on, right? So I want to make this session to be very interactive and a basic one so that all of you can also absorb, right? You can relate to the problems that you have studied. I'm hoping that you have ML background, right? The basics of ML and deep learning, right? Okay, good. So then I think we are fine. So yeah. Okay, but do you have, have you done any of, okay, then it might be a bit difficult, but I think you can understand a bit of applications maybe apart from technical stuff. But yeah, so ML is needed to understand why it works, right? So the topic is geometric deep learning for graphs and 3D point clouds. This is majorly what I work on, my lab works on. And the session is for 2 hours. We'll see, how much I can cover. I have a lot of content. How much I can cover, we'll see if we need 5-10 minutes break. If you all are okay, then we can continue without a break. Otherwise, I can give 5-10 minutes break. Okay. So these are the research interests, and these are the topics that I have worked on, let's say in my PhD, and in the last 3 years, I've joined IIT 3 years back. So I have worked on assignment matching problem on images where you have landmark points, let's say on both sides of the images. Let's say I take a picture of the scene from one angle and I take a picture of the scene from the other angle, right? We are taking a picture of the same scene, but the image would be distorted, right? Because it's from the different angles. Now can I find a correspondence between the landmark points in these two pictures? Right? It's a matching problem. And in general, assignment problem is a combinatorial problem, right? So I worked on this during my PhD. Then one set of students work on graph representation learning, which is more of, you must have heard about graph neural networks, right? Graph convolution network, graph attention network, and so on. So I have worked on, before GNNs, random walk based methods came. If you have heard about node to wake, deep walk, so on, right? And then GNNs came, like I mentioned, GC and GAT. Then there is another set of papers which is more on knowledge graphs, where it's not just the graph, but it also has some kind of information, let's say some text there, right? Some reasoning over some querying that we do on Google search, right? So Google has a graph in the background whenever we query, right? So then the other set is the 3D. So the half of my group works on the 3D data, which includes point cloud representation learning. I'll talk about what is point cloud. And also now 3D scene understanding, I'll talk about all of these. Work on self-supervised, few shot learning, and so on. I've also worked on spectral approaches and optimal transport, which is more like, if you've heard about earth mover distances, Wasserstein distance, right, and so on. So these are some of the things that I have worked on, have been working on. I would want to start with a general geometric machine learning, because the title says geometric deep learning. So what is the geometric machine learning? You have studied ML, but what is geometric ML? So the idea is the ML or DL, what you have seen so far, is more working on, let's say, images. You start with mostly images where you use CNNs, or you also use text, right? I'm sure all of you have been working on different problems, but mostly we say that whenever you ask someone to start with a DL, at least I say that just go with what MNIST data, CFAR data, and just do some CNN, right? So we say that traditional machine learning mainly focuses on the Euclidean data, which is basically a regular kind of data. Let's say regular means there is a grid. Image has a grid. We know that there is a location for the image that, okay, this pixel has this location, right? We cannot shuffle them. So that is a grid structure, which is, you can say, a 2D data. Then the text is a sequence, which is a 1D data, because you have sequence of words, right? You don't have 2D, you just have 1D. Now the idea is do we have data which is beyond 2D, right? So we say that geometric machine learning aims to generalize for methods, for data which is beyond 2D or let's say 3D or higher dimensional or graphs. I'll talk about why graphs we are talking about, manifolds if you have heard the term, right, and so on. So if I'm working on graphs 3D or beyond 2D, then I say that I'm working in geometric machine learning, because the idea is the meaning of the Euclidean data means what? Can any of you guess? What do you mean by Euclidean data? I think all of you know Euclidean distance, right? Can you guess what is the Euclidean data? I mean, the term is a bit different than Euclidean distance or a Euclidean domain, like it's mentioned non-Euclidean domain, right? So, anything? Sorry? No, not really. So the idea is, so let's say I'm considering a 3D data, right? The idea is, if I find out that, okay, what is the distance between these two 3D stuff? How do you find out? The easiest distance is the Euclidean distance, right? We can still apply Euclidean distance on 3D, but the idea is when you go beyond 2D, Euclidean is not always the best, right? So Euclidean data means you know that the shortest distance between 2 points is always a Euclidean distance in 1D or 2D, not beyond that. In 3D, there might be something else. Line is not always the best distance, right? Because there is a third dimension. It might be a curve, right? So 3D can have a curve, which is a distance, which is a geodesic distance, we call it, right? So we say that you can still use Euclidean distance. We also use Euclidean distance sometimes, but the idea is these areas are called as non-Euclidean domain. That means we are working with non-Euclidean data, okay? So I hope this is understood that traditional machine learning focuses on 1D, 2D, but geometric ML focuses more on, like, say, beyond 2D, high dimensional graph and anything, right? So the examples are like this. For example, social network is a graph, right? Regulatory network is some gene regulatory network from bio, then retail network is from e-commerce, right? E-commerce graphs that you can make of user has purchased an item, right? Then functional network is again something from bio. 3D shapes, I'll talk about that. 3D shape has different kind of representation. It has point cloud and meshes and so on. And again, some biological networks, right? So these are the examples. Now some of the applications, I think I'll be talking about a lot of applications so that you can understand, you can relate to why I'm talking about all of these. So for examples, I'm saying that one of the tasks in graphs is a node classification in graphs, right? Node classification in graph is more like, let's say you take a social network and you say that what is the category of a node. And a node can be a person. You can say, for example, you can say that what this person talks about on Twitter or X, right? So you can do a topic modeling on that. This is just one example I'm talking about. There can be many examples. So node classification is one such task that we do, right? So for example, you know that you divide your data into train, test, right? So here the gray nodes are test nodes, right? Colored nodes you already know, and then you predict for those nodes, right? This is what you do. This is node classification. The other one is link prediction, where you say that how highly likely it is that two nodes are connected, which is not connected right now, right? Two nodes are connected which are not connected right now. So can you find out a link? What is the probability that these two nodes would be connected? Example is Facebook. On Facebook, you get that people you may know section. How do you get that? That's a recommender system, right? They are recommending you. They are recommending you based on the basis of, let's say, mutual friends, some common things, right? So Facebook is saying that these two people should be connected because of some reason, because they have some similarity, that they have similar friends, right? So this problem is called as link prediction in graphs. Another one for 3D data especially, I mean there are many problems, but I'm talking about some of these. The other one is the 3D object classification and segmentation. So these 3D objects that you are seeing, these are called as point clouds. And point clouds are nothing but a set of 3D points, right? So you have only so let's say you have n points and you have 3D coordinates, so you have n cross 3 matrix, right? So this chair would be represented by this kind of matrix where you have x, y, z values and you have points from 1 to n. I'm saying that there are, let's say, 1000 points in this point cloud. Then you have n equals to 1000. That's all how you represent in the code, right? So these are the point clouds. Now you say that, can you do a classification or segmentation here? Classification, it's an object classification, simple classification that all of you know. That, okay, you want to classify that there's a chair, there's a car, table, aeroplane, right? Segmentation is another task where you segment their parts. You say that, okay, this is the leg of the chair. This is the backrest of the chair. This is the seating area of the chair, right? These two are the wings of the aeroplane, right? So this is called as segmentation, where you are segmenting the parts, right? This is a very popular task. This is also there in image, if you have heard about image segmentation, right? Yes, yes. So this is for a particular object. You can also do it for a scene. If you have, let's say you have an image. In a scene, what can you have? You can say that there is a ceiling, right? You can segment all of these parts. There are some, let's say, 5 chairs in the room in that image. Or there are, let's say, 2 cars in that scene, 2 trees in the scene. So they would be segmented with the same color, right? So the parts or the objects in the scene or in these kind of single objects, whichever parts are of the same class, that means if there are, let's say, 5 cars, all of those would be colored with the same color. There are some figures I have, we'll take a look at it, right? So this is some idea I'm giving you here. Then there is another example which I was giving in the first slide, which I was saying that I worked on matching problem, right, on images. So this is the figure from one of my papers where you say that you take a picture of a house from one angle and the other angle, the house is a bit rotated here. Now can you say that the point on this window matches to the point on this window? Can a machine say that, right? So the idea is, I mean, sometimes I have heard that some people say that this is an easy problem, but this is not an easy problem. I can say this very easily, but machine doesn't say that, doesn't match it very easily. It's a very difficult problem, right? So how can you match? Because sometimes there is occlusion in one picture, sometimes the point is present in one but not in other, if you take from different angles, right? And there are so many points, how do you connect some points, right? So this is another problem. Okay, now challenges of geometric machine learning. We usually say that when we go beyond 2D or when we work with graphs, 3D or manifolds, there are many challenges which are not there in 2D or text or images, right? Why? So I'll talk first about, let's say, the graph. Do you know, all of you know graphs, right? You have set of nodes and vertices, right? So if I give you 2 graphs, can you tell me what is the distance between 2 graphs? Are these 2 graphs same, right? But the ordering is different, right? So there is no sequence which is there, let's say, in 2D image, right? In 2D image, you know that this pixel is always there. So here you can shuffle. If I say that this is A, B, C and this is also A, B, C, but the node representation is different, right, in both. So there is no ordering. So we call it that they are unordered. Same with the point clouds. There is no ordering, there is no fixed ordering for point clouds. Right? When I was talking about set of 3D points, you can shuffle them. So same thing here. Now, in image, you know that for every pixel, what is the neighborhood? You know that, right? When you apply a filter. Can we fix the neighborhood in graph? One node can have one neighbor, but the other node can have 10 neighbors, right? So this term is called as unstructured. So graphs or even 3D point clouds are unordered and unstructured. These are two properties. And there is another property that we call it as they are irregular. Irregular means the image has a grid structure. That's why they are called as regular data. Right? So they say that this data is in regular domain because you can actually apply some filter or some convolution operation or something on the grid itself. But here, there is so much of irregularity that you can see this is a dense region, but this is a very sparse region. This is not regular, right? So there are sparse as well as dense regions. The neighbors of every point in point cloud or a node in a graph would vary. There is no fixed neighborhood and they are unordered. The ordering is not fixed. So there can be a problem of permutation invariance when you shuffle, right? So if you shuffle pixels in image, what can happen? Do you know this problem? When you rotate the images, can CNN still generalize? Do you know? If CNNs can still generalize if you rotate your images. Let's say you rotate your images and you feed in CNNs. Would it still give the same result? I mean, ideally it should, right? It should not matter that whether they are rotated or not, right? At least from our intuition, we say that whatever it is, either it is rotated or not, it should be able to detect. But do they generalize? So there's a very old problem that they are not rotation invariant. CNNs are not rotationally invariant. Nowadays, there might be some solution to that, some powerful, all these transformers and all, but when CNNs were started, when we were also working on CNNs, then it was not rotationally invariant. So now if let's say I am taking some model, graph model or a point cloud model, let's say I shuffle my nodes, then what happens? I mean, it would predict something, let's say node classification it would do, or point cloud classification it would do. Now I shuffle and then I see whether the result is same or not, right? So the idea is we need a network which is permutationally invariant, right? It should not be the case that if you change then the result should be different, right? Otherwise, this is not a great idea, right? So again, I'm repeating that the point clouds for the graphs, it's also the same thing. They're irregular, unstructured, and unordered. Okay? So this slide says that traditional machine learning methods can't parse non-Euclidean data correctly. That means these graphs and all cannot be directly applied with the traditional machine learning, right? So for example, even non-deep learning methods, how can you apply, how can you use graphs for those, right? And can you find out, let's say I've mentioned that, can you find out distance between two graphs? How do I find out, okay, easy question. How do I find out distance between two images? What can be the solution? Anything that you can think of. I mean, don't think that it's a simple answer or something. It's a very simple answer. Comparing? Okay, yeah, one solution is that, yes. What else? Anything better? I mean, pixel comparison is also right, but in terms of quality, actual thing that what is there, because it would work on the color part, right? The intensity of the pixel intensity, right? But what can be done? Yes, so that's the pixel difference, right? Okay, but on the pixels, right? Yeah, okay, so on the pixel you can do different operations, can do some, right, so this is the next level thing that, okay, you don't do just pixel comparison because it's just based on the pixel intensity, but you do a better comparison where you have better features. For example, edge features if you do, right? Anything else? Something related features? Because this Kenny edge and whatever edge detector is coming from the traditional ML, right? Anything from deep learning? Exactly. So comparing embeddings. So if you have embeddings, so if you, let's say, pass image to a CNN, right? Then you'll get some embedding vector, right? You'll say that, okay, I'll get some, let's say, 128 size vector for one image, I1, and I would get 128 size vector for, again for this, so you can take that, this as this, right? Now how do I compare? I can simply find out Euclidean distance between these two, okay? Why am I saying this is better? Because if you will give an option to a person that from these three, the person would pick this because this is the latest one, right? Otherwise, you can use any of these, whatever work for your data, right? So, if you cannot find out how do you compare two things, you always say that I want an embedding. When you say that, what is the similarity between two words? You will find out a word-to-vec vector for that, right? Word-to-vec embedding for that. You will say that I would take word-to-vec embedding for this word, for the other word, and then I compare them. Right? This is what you do. Similarly for graphs. Now, at least we agree that I cannot find out the distance between graphs directly, right? Yes. So there is this thing that for graphs also you will need embeddings again for comparison, right? Now there are 2-3 ways. One way is like you are saying. So it depends on the network. So some networks work on the node embeddings, that you learn node embeddings, right? But you can always consolidate all those node embeddings and say that I have just one vector for the graph. So you'll get G1 vector, you will get G2 vector, and then you can compare, right? So if I ask you on a scale of 0 to 1, right, these two graphs, how far are these two graphs? Can you see the difference here? There is the difference of only one edge, right? But what do you think, are these graphs very different or similar? So even with one edge, the graphs become very different, right? So if I give two graphs, I'll take the embeddings and then I'll say that, okay, let's say maybe these graphs have the distance of, let's say, 0.6 or 0.3, anything, right? So we say that we made this problem easier by saying that, okay, I am embedding a graph because I don't have any embedding to begin with. The graphs do not have any embedding generally. So I will embed this graph, then I'll use those embeddings. This is the answer for the processing the graph or any higher dimensional data, even for the 3D also, right? So now the idea is why it is in the challenges is it's not very straightforward. There are many methods. What do you use? Right? So there is no fixed answer to how do you find out distance between two graphs. There are millions of papers that you'll read that, okay, some paper says that our method is the best, the other. So that's why this is a challenge, because there is no correct answer or a fixed answer to it. Okay, let's move on. So I have given you the idea of what is a geometric machine learning. I'll begin with the graph and we'll see, it depends on the time, how much I can cover with the 3D. Okay. So graph is represented something like this, and when I'm talking about graph, I'm talking about undirected and unweighted graph, because you can add more complexity like directions or weights and something, but whenever I'm talking about graphs in the next set of slides, it's undirected and unweighted. And I hope all of you know that graph is represented by adjacency matrix, right? Because you should connect this to how do you write it in a code. So in code you process adjacency matrix, right? Okay, so that was a graph. now this is a knowledge graph which I was talking about. So the methods which are like graph neural networks, they mostly process on the raw kind of graphs where they don't have any extra information mostly. They might have, but not really. Knowledge graph is, it is full of knowledge. I mean, it has a lot of these things. If you see, George is a person, something works for something, right? So this is mostly used for retrieval, question answering, right? So I'll tell you that GNN is one set of area of research and knowledge graph is one set of area. They both are related because they use graph, but they are very, very different. The papers are very different, right? But I'll talk about both so that you'll get idea. You can always pursue it later if you're interested, right? So we are saying that knowledge in graph form capture entities, types and relationships. Entity is nothing but a node. Relationship is an edge. And type is some type of node and edge. I'll talk about that. For example, this is a city, right? But this is some company maybe. This is some person. So we are saying that the nodes are of different type. For example, on Facebook, if you make a graph of Facebook data, Facebook also has a graph, they create graph, Google also has it, right? So we say that on a Facebook graph, the node can be a person, so I can be a node, right? And then groups, pages can also be nodes, right? On Facebook graph, all of you agree, right? Groups and pages can also be nodes, because then they'll say that how many other nodes, other people are connected to them. So whenever we say that there are more than one type of node or edge, it is called as heterogeneous graph, right? So if all of these are of the same type, I'll give you an example which would be coming in the, I think, the next slide, is if all the nodes and edges are of single type, it's called as homogeneous graph, otherwise it's called as heterogeneous graph, right? So I've already mentioned nodes are entities, nodes are labeled with their types. Edges between two nodes capture relationship between entities, which is an edge, right, typically. So this is an example. Now why graphs? Why this hype? Because the idea is, whenever someone asks me why do you think the graphs are good and why do you work with graphs, I say that you give me any data, I can convert it to graph. So I want you to connect this to your tabular data that you have started with in machine learning, right? So let's talk about that, because I want you to connect with that, right? So you have what, rows and columns, right? You have, so when you started with machine learning, you have these rows and columns, and you say that, let's say these are your some feature 1, feature 2, and feature 3 and some class, let's say label data, and you have, let's say what, data sample 1, data sample 2, and right, that's how it was. Now when I talk about graph, a node in a graph is similar to a row in a tabular data, right? Because whenever I make a graph, whenever I make some graph, I would usually say that when I train this using some neural network, I say that I need to begin with some feature vector if I need an embedding of a node, right? Because eventually the learning on the learning using GNN is you eventually get a node vector. So when you get a node vector, you begin with some node vector. And how do you begin with some node vector? Either you initialize it randomly, or if you already have some feature from the data. Sometimes for some text data, you have some, let's say, one hot vector encoding, and by the time it goes to different layers, it gets updated, it gets better, right? That's your node embedding that you get in the end. But if you do not have any node vector to begin with, sometimes say, for example, there are some data sets on road network. How do you begin with the vector? How do you initialize your vector? So then you can always initialize randomly, or you can make your own, you can create your handcrafted feature, or anything you can do, right? So you say that this is similar to a node, right? So every row is every sample is some node here. This is a general setting. The only difference is what? The edges? Yes. So this feature would also be there. So this is also there as feature, this is also there as feature. So features are at both the places. The only difference is, let's say when you work with this, what is your aim? When you work with the tabular data and you apply some machine learning model, what is your aim? What is your end goal? Prediction. But to predict, what do you do? Learning, right? That's what you are doing, right? And how does the learning happen? How does it happen? Training data. So you have a forward pass where you find out, you do some prediction, you get a loss, right? You compute the loss function, right? And then if you're based on the loss, the things would be updated so that it gets improved. It should be closer to your the final prediction, right? So if your loss is 0, then what happens? Okay. So if your loss is 0, that means everything is best, right? Then there is no update. Then you are at the best stage, but that can be an overfitting because it might not generalize to the unseen data, but that's a different case. Yeah. So whenever we do learning, whenever we say that I want to learn my model, I want to train my model for this data, right? The underlying thing in the model is basically it is finding out patterns, right? All of us are doing pattern recognition in some sense. So if I intuitively say that I'm training a model, let's say my model would say that, okay, in D1, D2, maybe feature 2 are same. Their value is same, right? Or maybe let's say they are also same. Maybe might be a different, but at least 2 features are similar. So this is what they find out, right? They find out pattern that what features are similar for which data sample, right? So we are doing pattern recognition in some sense. But there is no edge here. We are not giving an explicit edge that D1 and D2 are connected. Whereas the difference between tabular and this data is we are explicitly saying that these 2 nodes are connected because of some reason, right? Now because of some reason is what? Some reason can be 2 nodes might be similar, right? So usually what happens is there can be very different answers for different graphs or data, but I'll tell you the connection means something. If there is an edge, that means there is some similarity or something in common, right? So I say that these 2 are connected maybe because their features are same, or they are connected to some common neighbors, right? Or their structure is same, their some property is same, right? Their meaning might be same because there is a structural similarity, there is a semantic similarity, right? So all of these things are there. Now, when I'm saying why do I want to use graph? I can do the same job with the tabular data also. Why are we going towards graph? We are saying that all of these many bio papers, they are constructing their data into graphs. In fact, social network and all of these. Social network, even retrieval, image retrieval, the information retrieval is happening with graphs these days. Why these graphs? So just to give you an idea is, we are explicitly giving some information that they are connected, whereas this needs to find out the pattern. So there again we need to find out some pattern, but at least some explicit information. So basically an extra information there, that's all, just to simplify this, right? So we are saying that graphs are a bit better because they have an extra information, and especially structure. We are saying that we are studying the structure of the data. Okay, that's where the term geometry comes. I mean, whenever I say geometric machine learning, that's the idea. Okay. Now there are some examples I have, which are, let's say, social network. All of you know, right? Node types can be any account or any post, channel or anything. Depends on different kinds of social network. Then there can be different relation types. You like, you comment, right? So you join some group. So those can be edges. So this is one example. The other example is this bibliographic network. So all of you know that there are research papers, one author cites the other author and so on. So these are called as citation network, right? Citation network is either you can make graph like A, which is a co-author homogeneous network where you say that all the authors would be nodes and authors are connected if they have cited the other author or an author is cited by some other author, right? But here the nodes are same, that there is no type, so it's called as homogeneous network, okay? There is no other type of node, whereas the right side graph is a heterogeneous network because this is also a citation network, but that network says that this paper is cited by this author, so paper is also a node, an author is also a node. This paper is published in this conference, which is also a node, right? This paper is published in this year, which can also be a node, right? So multiple types of nodes and edges, so it's a heterogeneous. The bibliographic network has some few data sets that are very popular that we use for research. Yeah.
Cyber, OEG, other things like scientific research.
Yes, yeah, scientific publications. I have some tables later which mentions the data sets that we use for GNNs. But yeah. Then there are molecular graphs, because I was saying that you give me any data, can we convert it into a graph, right? Molecular graph itself is a graph, but can we consider it as a graph that we study, like G equals to V comma E, right? Set of nodes and edges. So this screenshot, might be a bit blurry, but I took it from some paper because I found it interesting. So they said that there is this molecule of acetic acid. If I study it as a graph, what do I need? I need that what are the nodes, what are the edges, and to begin with, we can have a node feature matrix that we can build. If we cannot build, we can also ignore, but we can build. So adjacency matrix that they have made, that which node is connected to which node, right, which is a simple matrix. And then you have a node feature matrix where they added atom type, they concatenated it with some formal charge and some other feature, right? So molecular graphs have the atom type, valency, and so on, which you can concatenate, which you can add, and you say that, okay, this is a feature of a node, right? This is one idea of how do you construct a graph and consider a feature. Then they also made an edge feature matrix. Not all data sets have edge feature matrix usually, but they also constructed it because there are different bond types, double bond, single bond, right? So you can do all of these things based on your requirement, whatever problem that you are trying to solve, and what is the data that you are trying to use, right? So this was an example. I'm explaining all of this so that you can try to connect in the real world setting, that if you have any data, for example, let's say this class, there are many people here. Can we make a graph from this database if I get the details from you? We can make a graph, right? Based on something, based on, let's say, the courses that you have done, similar courses, or let's say, based on age, right? Based on year, batches, many other things based on demographic details, right? The diversity and all. So we can do all of that. This is another example where we are saying that instead of a normal molecular graph that we have seen before, can we find out a pattern in molecular graphs, which is like, can you find out some similar, we call these terms as motifs. Motifs is basically a pattern. So a subgraph. So I say that, okay, this is a subgraph which can be some other molecule, right? And this is a subgraph which is some other molecule. So I say that from all these molecules, I say that, okay, if these subgraphs are present in a particular molecule, that means they are, let's say, acidic in nature, because they are maybe from carboxyl group. So finding out subgraph is also a good problem. There are papers on that also where people find out subgraph structure in a graph, which is also a difficult problem. Because how do you find a subgraph? How big is the subgraph that you extract, right? This is again another problem or application, whatever you want to say. Okay, this is one more area, which is a very interesting area of scene graphs. This is a whole set of different area of research. So scene graphs are basically, you will see many papers on this. There are many groups in, let's say, in Stanford and other universities, they are working on this. This image is from CVPR 2017, where you say that I have an image and I want to construct a graph out of that image. How can I construct a graph out of that image? This is the one way. One way is you find out whatever are the objects in that graph. You do object detection so that you will get bounding boxes of that. Now, based on overlap of the bounding boxes, right, can you make a graph? Let's see this example. Okay, for example, you see that there is a man, which is a bigger bounding box. Now, inside this man, there is a shirt. So, man is wearing shirt, right? Man wearing hat, man wearing pant, has hand, arm 1, arm 2, and so on. So, there are many methods where you can actually extract a graph from these images. Yes? You can say, I mean, image captioning would give you word, yes. It can help you to give the keywords, but then you have to find out the relations, right? So, there are many methods. I mean, I don't remember any recent method, but I have seen these papers few years back where there was no DL method at some point. There was something called conditional random fields, if you have heard of. They were solving this problem using CRFs. But I'm sure there are DL or some other new methods that are there. But this is also a very active area of research. I'll give you an example. You do Google search, you write on Google that a person is sitting on a boat. What will you get? What will you get in the image tab? Lot of images where a person is sitting on a boat. How do they do that? They do using this, right? So what do they do is, you query something on Google, let's say, or on any search engine. They make a graph out of that query also. So they can make this kind of graph from that query, and they already have images in their graphs, or let's say in the inference time they can make graphs on the fly. Then they say that they get the embedding for query, they get the embedding for this, they find out the similarity, and they say that, okay, these are the best results, right? This is very useful there. So this is useful in image retrieval, or let's say whatever, especially searches. So this is a very good area. I mean, someone wants to work. Okay, so we have seen some applications, some examples. Now, what do we do? What is the aim? Because when I asked you that what was your aim when you were doing machine learning for some data, right? So let's say, what do we want to do if my input is graph? I do some machine learning on that. That means some architecture, some model. And then what do I want? So task, we know that we do node classification, link prediction. But what's the aim? What is, we don't want to use it just as a black box. We want to understand how this prediction is happening, right? So let me ask you one question is, when I was saying that you have, let's say, a tabular data and then you were feeding into, let's say, any multi-layer perceptron or any logistic regression, SVM or anything, you do some prediction, you use some loss function or something, but in the end, what is your exact goal when you were saying that I got an embedding? What is there in that embedding? Yes, it's a high dimensional vector. But what is the property of that vector? That what is that vector has learned? We know that there are only numbers. We cannot understand that. But machine, how does the machine know, right? When I'm saying that these two nodes are similar, are their vectors closer or are their vectors farther in the feature space? Closer? Okay, why? Why closer?
Because they have similar features.
Right, so the similar case is the word2vec. If you talk about train word2vec model, which is of 300 dimension vector, if you take two words of similar meaning and you find out the distance, their distance would be similar, whereas if you take two very different words, their distance would be larger. That means Similar things are closer in feature space and dissimilar things are farther in feature space. Right? Similar things mean similar meaning here, but let's say if you have two data samples from tabular data, the data samples which are of same class would be closer because you do TSNE if you have done TSNE, right? TSNE plot. So TSNE would say that, would give you the visualization something like this, where you say that all red label nodes are closer in the feature space if this is 2D, if 2D space is my feature space right now. And all blue are closer, violet are closer, but red and violet are far because they are of different class. So the whole aim of machine learning is that you want semantically similar things to be closer in the feature space and semantically dissimilar things to be farther in the feature space. This is the main goal when you are saying I am learning and embedding, right? And same is the thing here. When I am trying to embed this graph, and there are some labels because let's say we are doing node classification, there are some labels. So when I want to embed this, I want this kind of output, this kind of TSNE visualization where I say that similar nodes are closer, dissimilar nodes are farther. This is what we do in clustering also. That's how we find out clusters, right? So this is the whole goal, and this is the same goal here for graphs also. How do we take advantage of relational structure for better prediction? Complex domains have a rich relational structure which can be represented as a relational graph. So the meaning of these two things are, the aim is same, right? Semantically similar things are closer. The only idea is how can we leverage this graph structure, because we are not using tabular data anymore. Because I am saying from last 1 hour that graph is better. So I am saying that graph has some explicit links, information, extra information. So we are saying that we can take advantage of this structure because we are saying we have structure. Tabular data do not have a structure like finding out relations and all. They find out on their own. But here we have some structure. So we are saying that, okay, we leverage this kind of structure and then maybe our prediction might be better than the normal methods, right? So this is the graphs for machine learning, that we want to learn the embeddings for the nodes and want similar things are closer. Now, this is an interesting slide. So what happened was when graphs were introduced, there were some older methods that were before GNNs. Some older methods came that were introduced before GNNs. They are also very popular. They also do very well. But when maybe someone started to think that why can't we apply CNN kind of architecture to graphs, right? Or can we make a convolutional or operation for a graph, right? So this is one of the papers which what they did was they tried to convert a graph into looking like an image, like this grid. Because I told you that if you make your irregular data into a regular data, like a grid kind of structure, and you can apply convolution operation. Whereas our graph is right now an irregular data. So they made this graph into looking like an image. But is that always the case? Not really, right? A graph cannot always be like this. But this was an interesting approach, just to give some idea that, okay, we can apply CNNs if we make our graph like this. So they made a graph like this and they just simply applied CNNs. So this was a good idea, I mean, also to explore, but it is not sustainable for every graph. Okay? So challenges with graph is similar to what I have already mentioned, that there is no spatial locality like grids, so there is no regular structure. Arbitrary size and complex topological structure, so size of neighborhood is different for every node. No fixed node ordering, that means they are unordered. If you shuffle them, it might change something, but ideally the structure is same, right? So images and text look like this, and the graphs looks like this, right? Okay. So now, what is the deep learning for graphs? This is also the same thing. The only thing is the architecture, which is just the abstract version of some neural network, where we are saying that we have an input as a graph. If you see this graph, this is a homogeneous, you can say homogeneous, or this you can say two classes graph, right? And then you say that your output is some prediction, which is more like a predicting a side effect whether when you take two medicines, what is the side effect of that? There is a popular problem. And the idea is they say that instead of convolution, they have graph convolution. So when deep learning introduced this GNNs, they said that they made layers called graph convolution layer. We'll see that what happens there, but yeah. This is what graph convolution is, and the remaining things are similar: activation function, regularization, and so on. So this is the overall abstract version of the deep learning framework for graphs. Okay? And this is the main aim, which I've already mentioned, that if you have a graph, it would go to different hidden layers, and when you plot these, it should look like this, where same label nodes are closer and different label nodes are farther apart. Okay, so this is our aim basically. We want these kind of visualizations. Then we can say that, okay, it's a good quality learning. Right? Then if I have to say it mathematically, then I say that I want to map nodes to d-dimensional space. Right? I want to get some d-dimensional embedding such that similar nodes in the network are embedded close together, which I've already mentioned. And the mathematical formulation is this, that we want to learn a function where u is being embedded to some d-dimensional space. Okay? Okay. So this is clear, I think. Any questions so far? Anything that you want to ask? Yes. Softmax? Yes, same thing would be here. So whatever you have used as a last layer you used as softmax, right, for classification in CNNs or anywhere. Same here. Yeah. Yeah, depends on your problem, yes. Usually the general setting I tell you is people start with the node feature. You can, but the commonality is edge features are not always present, in hand already. So there are many networks, data sets that are there where you already have some node feature matrix to begin with, and then you update on that, right? So there are no edge features usually, but you can make your own. You can also say that I want to learn weights. Right.
Let's say I have two disconnected graphs. So
Okay.
I want to connect them. Without the randomness, we know the name, the brute force, and you have connected edges one by one, and then you are computing something. Okay, this might be the best approach to connect them.
Okay.
Without that brute, what other methods?
You want to connect them. But how do you want to connect? It's like a simple stuff, or you want to do some learning? No learning, right? For?
For detection.
For detection. So you want to detect that they are disconnected graphs? Okay. The easiest answer is you can do BFS, DFS, and then you can find out, right, easily. Right? But learning, you can do ideally, but again, you have to learn the feature vector for that, but I don't think that this is necessary to do any learning there, right? So I'll tell you, because now this has been brought up. Yes, there are many problems that people want to apply machine learning on, which can be solved without machine learning. So don't apply machine learning on, even industry people apply a lot of machine learning on some things which can be solved without machine learning. So don't complicate something. That's one example, but that was a good question. But in general, I'm saying that you should always think, if there is a real world problem, that can we solve this without machine learning? Then just do it with that. And if not, just go with, whatever method that's there, right? Okay. So anything else, or should I move on? Okay. Okay, so I'll move on then. Yeah, so these are some categories of tasks. I think I got one question, so let me ask you this question before I move ahead. I have shown you that CNNs for graph, where that paper has converted the graph into a grid kind of structure, right? This, right? Now, can you think of any other way where you can apply a convolution to graph? Simple convolution, CNN. This is very simple if you just think of it. So this is one way, this was one way where they converted graph into a grid kind of a graph, right? Anything that you can think of? Okay, how can you apply CNNs to graph? In a raw form of graph you cannot apply.
Embeddings, you type for the embedding of each node and then connect them and then.
No, I think. So where do I apply CNNs? Yeah, what is the input? Image. So can you convert your graph to image? There's a hint, but a very bigger hint that I have already given, but yeah. How can you convert your graph to image? Let's think about that. No. Graph to image means you need a grid. You need, like, let's say 228 cross 228 kind of dimension. Yes. So how do you do that? How do you get RGB from graph? Yeah, but how do you map this to a graph? A graph, weight of the? So weight of the edges you are saying you will put into pixel or? Okay. And what can be a node? There. What can be a node there? So the graph that we study is basically this, right? In data structures, we study this, or any graph theory, where V is a set of this small v belongs to this bigger set, and then this belongs to this set, right? Okay, that is also a good answer. I mean, this can be one possibility, yes. Yes. That can also be one possibility, but then you just fix your graph. I mean, it's just zeros and ones. So CNNs are more good with pixel values, so there won't be any pixel values. But so in terms of the grid, yes, is the right answer, but practically it won't work, unfortunately. So so the graph that we make here, right, you can shift that graph also, right, and this node can go there, right. Let's say if you give this graph into my hand, I can say that I can just mold, right, move those edges and so on, right. So it's not fixed in any space right now, this graph. Exactly. So yes, right. So basically you want to embed, the answer I was expecting was you want to embed a graph into a 2D space. This graph, general graph is in no space right now. Unless you say that you have a d-dimensional vector, or can you embed this graph into a 2D image? Can you embed it into 2D space? For example, the TSNE that I was showing you, right? Yeah. This is a 2D space. Now I say that, okay, I'll connect this because of using something. Let's say distance. I'll say that I'll make a KNN graph. Can I make a graph? Yes? And now when it is in 2D space, you can just apply CNN. I mean, that's also not very good in performance, but this is one idea I wanted to give you. You can embed your graph into 2D space, and there your node would be having some coordinates. So your nodes are fixed. And that is called as geometric graph. When your graph is embedded into some space and it has coordinates, so that you can also find out the distance which is on the edge. Right now there is no distance on this edge, right? But if you can find out a distance on the edge because they are in some coordinate space, then it is called as geometric graph. I mean, this is a formal term that we use, okay? So this is a graph, but that can be a geometric graph, okay? Yeah. Yes, can be anything, depends. This is just one example. I mean, if you think of it, there can be other things. How do you solve this? Okay. Now coming back to, we have seen what is the aim, why are we using graphs, right? We have some applications, right? What is the learning that we want and so on. Now what are the tasks that we perform? I've already mentioned a couple of things, right? So there are node level tasks, which I've mentioned, node classification. There is this edge level task, which is a link prediction task, right, which is on the edge. There is a community level, which is a subgraph level. This is called as community detection, if you have heard of. This is this community level task. And then there are other set of tasks which are based on graph level. So there is something called graph classification also in GNNs, right? So you have node classification and also graph classification, and you also have graph generation. How do you generate graphs? So very simple application is social network, but social network would change over time, right? Okay, so this is a graph generation, that is a graph evolution which I am talking about. That is also a graph generation, but not that graph generation which is like generating some new graphs. But the idea of graph generation is you have some data, you generate graphs from that. For example, scene graph is a generation task. From image you generate graphs, right? There is something called graph evolution also, where you study the sequence of graphs, how your graph is evolving over time, which is more like social network. Because today social network is of this size, but tomorrow it can be a bigger size, it can change, the edges can change, the nodes can change. So can you study the pattern? So which is like a time series data. So it is called as temporal graph data, if you have sequence of graphs. Right, so these are the tasks which is there. So node level is node classification. The example is this, predict a property of a node. So categorize online users and items, right? E-commerce. Link prediction, predict whether there are missing links between two nodes. Example, knowledge graph completion, which we were looking at, whether this person is from this city or something like that. Graph classification, categorize different graphs. This is very popular in molecule property prediction, where you have multiple molecules, molecular graphs, and you have some labels for that. So if you understand this problem, what is your input in node classification? Because we should also understand, right, what is your input output. So output is some prediction classification label. In node classification, you are processing only one single large graph, which is like social network, right? Or maybe citation network. Whereas in graph classification, you have multiple graphs, because that's how you find out label for each graph, right? Otherwise, how would you find out? So just remember that for link prediction and node classification, there is just one single big graph that you process, and you work on node and link level, whereas graph classification has multiple graphs because you want to classify those. Clustering is like a community detection that you do, right? Graph generation is, yeah, drug discovery is one interesting problem where in bio domain, people find out different combinations of let's say chemicals, where can they generate some new medicine or new drug. Yeah, that's a very good example, and they have a very good blog on that. AlphaFold, you can look at, think by DeepMind or Google, yes. Yeah, so you can look at that. So graph generation is very useful in drug discovery these days. People were saying that without these GNNs and all, they used to take some decades to create new drugs because they were playing with all the combinations and so on. With graph generation, they generate new graphs, like GANs generate new images, right? So they generate new graphs, and then these new graphs would be tested in the labs, that whether these are making sense or these are valid molecules or not, or can we make this into drug, how would this be useful, and so on. Okay? So it's graph generation, graph evolution, as I said, like a time series data. How can you study that, right? Can you say that I have 10 graphs in sequence, can you predict an 11th graph? So this is like video frame prediction. You have a video, you predict the next frame, right? Something similar here. Okay, so these are some tasks. I hope, I mean, you are able to connect this to real world, right? Yeah, okay. So I think we have some more applications. So this is one of the very popular problems in bio, polypharmacy side effects, where they are finding out, if you see this is a heterogeneous graph. This is protein node and this is a drug node, right? So they are finding out that if you take these two drugs together, toxicillin and ciprofloxacin, then what is R2? What is your side effect? So they are predicting the side effects here. If you take two drugs together, then what is the side effect? There are papers on that. This is called drug repurposing, which started, I think, again, I mean, was a hot topic during COVID. So repurposing is drug discovery is something which you discover, which is new. You are generating new drug molecules. Here, people are, I mean, this paper says that there are already existing drugs, maybe which are not useful. So can the existing drugs be useful for some new disease, which is like COVID-19? So this is some COVID-19 paper, where they were finding out, can you reuse some drugs for COVID or any new disease, right? So they were finding out combination using graph, they were making graph out of that. Then this is traffic prediction using GNS. This is also this by DeepMind, very good blog on this. You can look at this. So the problem is, all of us use Google Maps, right? And then we check that what is the ETA, estimated time of arrival. And at least I feel that it's almost fine. I mean, with Google, the estimation is usually fine, unless it's too much of traffic. So what they did was, they said that, okay, ETA is still not great. So let us solve this problem using GNNs. So what they did was, if you see this figure, they say that how do you make your road into a graph? Because your road network is not the network, like if this is some landmark and this is another landmark, straight line cannot be a road, right? There might be some other way that you will do, you will move to different roads. So it's not very easy. So they said that they took the road maps and they converted that data into graph data by using super segments. So they said that I'll take a patch of a road and that patch would be my node. Because you need nodes and edges for graphs, right? So they said that, okay, let's say, I'm just giving an example, let's say take a 500-meter patch and this is my node. And then again, new 500-meter patch and this is my node. And now based on the which comes next to which, you connect them, right? So now you make a graph like this. So from super segment you make graph and then they apply GNNs, right? And then they predict ETA for every node. That means you predict time, that how much time a person would cover this patch, and then you sum up everything. So something like that they did. You can look at it in detail on the blog. And their claim is they improved the ETA. It might be the case that Google has maybe this, I don't know, right now, yeah, in their maps. Okay, some popular graph datasets that we use. So node embedding datasets, because I have mentioned that for node and link level, we have one single graph that we process, and for graph we have multiple graphs. So these are some popular datasets that we use in papers. Block catalog, and you can see the cardinality, how big is the graph. What is the size of a graph based on the number of nodes and edges. And I'll talk about this. These are the number of classes. This is basically a feature vector that they begin with. They say that, for example, in Cora dataset, they have 1433 size feature vector for every node that they initialize with, and then it would get updated, right? This is graph embedding datasets. These are mostly some molecule related datasets. If you see, let's say except this maybe, or maybe collab. And these are average number of nodes in every graph of this, and they also have, let's say, 188 graphs in this dataset and So this is number of graphs, but there is no number of graphs here because it's just one graph. Okay, so this is just to give you some names that we use these. Then because KG is a different set of papers, KG knowledge graphs use these data sets, Freebase, Wikidata, DBpedia, and so on. And usually knowledge graphs are super large, very, very large data set. So they are massive, they have millions of nodes and edges. And we usually say that KGs are usually incomplete. Incomplete means there are some missing links. So a very popular or still an active area of research, a very old problem is called as knowledge graph completion, where people find out missing links in knowledge graph, they try to complete it. So it's an active area of research, and it's also an old problem, not very new problem, but because they say that this is so big, because they collect these kind of data. So they say that whenever you collect any data, it would definitely be having some noise, and it would not always be complete, right? So they say that knowledge graph completion, knowledge graphs are always having some missing links. So this is some kind of example of knowledge graphs where you say that there are some nodes and edges, but let's say this link is missing. So you predict this link, right, and complete the knowledge graph. So here what they say is, how do they predict? They say that for a given head-end relation, that means given one node and an edge, can you predict a tail node? This is called as relation prediction. This task is called as relation prediction task in knowledge. These papers came into the world. Basically, this is the GNN era, but before GNN, there were these deep work node to vec that are random walk based models, right? Now what is a random walk? You have a graph, you start with a node, you say that what are my neighbors, what are all my neighbors, and with uniform probability you move to some other neighbor randomly, okay? And then you are the second node. Now with uniform probability, you move to one of its neighbors. So you get a sequence, something similar to BFS, DFS, right? Whenever you go with, let's say, BFS or DFS, you don't define that to which neighbor you will move. You will randomly move to one of the neighbors, right, with uniform probability. So using those kind of sequences, random walk sequences, they introduce this deep walk and node to vec. Okay? So these are very good. I mean, should definitely go through it if anyone wants to work in this area. Then there is a GNN era, which is based on graph convolution network, and then also graph attention network. Graph attention is the same attention which all of you might know, attention transformer, right? Attention is all you need paper, right? And then this is a different set of era, which is knowledge graph embeddings. But knowledge graph embeddings also, it was also solved with non-graph models, trans E, trans R, all of these models. So initially these models came in which were not leveraging any graph structure. Then after GCN, there was something called relational GCN, which was made specifically for knowledge graphs. This was introduced, and then it performed better than the non-graph. Yeah, so in GNNs you can use GCN, Sage, GAD, there is GIN. So there are many others, depends. I mean, GCN and Sage I have seen people use a lot. So, okay. Then there is something called, okay, then what is basically a graph neural network? What is the crux behind it? So we say that, whenever I say that, what is a graph convolution? All of us know the convolution, which is a filter you apply on image, you do convolution operation, you take all the neighbors' information, and then you do some pooling. Similar to that, there is something called graph convolution, and to understand graph convolution, there is something called message passing mechanism. To perform graph convolution, we say that we do message passing mechanism to finally apply graph convolution layer. Okay? Now what is this message passing mechanism? It's a very simple idea, very, very simple idea. Let's say I am a node and I say that I am represented by whom I connected to. Usually that's the case, right? I look at the neighbors. That's why people use KNN graphs and all, right? K nearest neighbor, using that you do classification also. So I say that I am a node. There are some neighbors around me. So I want to use their information. And then I would do something and then I say that, okay, this is my new representation. Because eventually we need to learn some representation, right? So how do I start with? I begin with some feature vector, which I already have, let's say random or some given. Now I say that in first layer I take feature vectors of my neighbors, right? All the feature vectors of my neighbors. I do some operation, let's say mean or max, whatever pooling I do. So I aggregate these feature vectors. So I get a new message. This is called as message. Now this message, and I also want to retain my previous message, otherwise I'll lose my information, right? So I take information from my neighbors and I aggregate those information, right? Before aggregation, we also do linear transformation, which is learning a weight matrix, right? So I take X and I do WX over that and I aggregate, and after aggregation, let's say I concatenate my previous feature vector. So this is my new feature vector and I say that, okay, this is my layer 1 output. I'll show you one I have.
In this, the calculation will be getting repeated, right? The computation redundancy and the repeating requires.
Yes, yes. No, but you are aggregating this, right?
Let's say we started from A, then we are in the bottom again we are on A, right? Let's say when you're random walking, see, when you started from A, then you're going B, C, D, then in B you're getting again to A and C, then again A, the graph will continue.
Yeah, so it won't continue, depends on the layers, how many layers you, right? So for one GNN layer, so let's say you have this node A, and what are the neighbors of A? B, C and D. These are the colors if you map those, right? So you say that you take these messages, this is a message, and before aggregation you do this a neural network box, because if you want to learn neural network then you need weight matrix, right? So you do linear transformation on those messages which are feature vectors, then you aggregate. So first step is message, take the message, aggregate those and then finally concatenate. This is a GNN layer 1, only one, right? You do the same thing for every node, which is fine, right? So you do the same thing for every node in layer 1. That means every node is getting information from their neighbors and aggregate and get the new representation. This is fine, right? There is no doubt. Now, so how do I take? I say that I take my previous feature vector, which is this HV coming from layer L minus 1, right, which is the previous layer. So I am a node V. I take feature vector from my previous layer L minus 1 because I want to retain that, otherwise I'll lose my information. And then I take features, the messages or features from all my neighbors U, which are coming from the set of neighbors of V, right? So all my neighbors which are U, and then these are the two things. You aggregate these information and then you concatenate. So these are the things. You have message from every neighbor and you transform it, right? This is your message after transformation, right? And you do aggregation using sum or mean or max, any kind of pooling. And that's when you get this aggregated vector, right? And finally, you concatenate this to your own message, right? So this is a very simple idea, right? Take information, linearly transform it, get messages, aggregate using sum pooling, max pooling, mean pooling, and then you concatenate with your own. This is the whole message passing. Now, the main thing is, yeah, that is a problem, but before that, Now this is one layer of GNN. Let's say I apply 2 layers of GNN. Then what do? I do this same operation in layer 2 also, right? I'll do in GNN layer 1, I'll do the same operation in GNN layer 2 because in GNN layer 2, my neighbors are also updated. So the new information is coming, right? Now, I do the same in GNN layer 3 and so on. So how many layers should I go with? So I'm sure you must have studied deeper layers are better, right? At least in CNNs, right? You go deeper that's why the deep learning it says. But this is ulta in GNNs. You don't need many layers, otherwise your model would not do well. So what is the problem? Let's understand that. Let's say in GNN layer 1, you take the information from neighbors, right? Which are the raw information right now because it's just the one hidden layer. In GNN layer 2, you take information again from the neighbors which have already taken information from their neighbors in GNN layer 1, right? So in some sense, in GNN layer 1, you take one hop information. One hop, two hop, you understand, right? One hop neighbors, two hop neighbors, like length 2 neighbors, right? So in GNN layer 1, you take one hop information, but in GNN layer 2, you take 2 hop information indirectly, right? Because you take information which already have taken some information in previous layer. Then in GNN layer 3, you take information from 3 hop neighbors, indirectly, not directly. So we say that as you go deeper into more GNN layers, you take information from n hop neighbors, which creates a problem. Now what is the problem? Ideally it might be good because if we talk about CNNs and all, they are good. So there is a problem called over-smoothing if you take many GNN layers. I'll talk why. So stacking of GNN layer is a problem. It's called as over-smoothing problem. Now why there is a problem? The problem is every node was differentiated by its neighbors. Who is around me? My differentiating factor is that. If I'm connected to 10 nodes or 5 nodes and what kind of connections I have, right? Whether I am connected to some similar nodes or some other nodes. Now if I'm let's say considering 5-layer GNN, I'll take 5 hop information somehow, right? So every node will get 5 hop information. Every node will get messages from 5 hop neighbors, right? That means, do you agree that the neighborhood overlap is so high? Right? If I take this node, I take neighborhood, district, there would be so high overlap if you take more number of layers. If the overlap is so high and the overlap goes to some extent that on roughly all the neighbors are same, let's say for every node. So identity is lost, there is no differentiating factor. Your vector that you learn is not distinctive. All will be generalized to one representation in the TSNE or whatever feature space. Right? Do you agree? This is the figure actually. So you say that you take one, so this is your node of interest, that means you are talking about one node. You take one layer GNN, that means the neighbor of this node are only these 4. Maybe we cannot see it, but yeah, these are the. Now you do 2-layer GNN, the neighborhood becomes larger for this node. And for 3-layer GNN, the whole graph is the neighbor of this node. That means for some other node also this is a similar case. So neighborhood becomes similar for every node at some point after a few layers of GNN. That means there is no distinctive factor and all the feature vectors are similar, which is not a great idea. So usually I don't have correct answer to this because people usually ask me how many number of layers do you suggest. So there is no correct answer I have, but I usually say that it all depends on data, but at least I haven't seen that we go beyond 2 or max 3. It also depends on the size of graph. If your graph size is so large, then you can go with let's say 2, 3, I don't think beyond 3 in fact. 3 is also a very good number because if your graph is dense, what is the meaning of a dense graph? That means you have many connections. Yeah, all are ones is a complete graph, but when we say about dense, so we say that many connections are there. So if you talk about nodes to edge ratio, it is very high, right? Whereas if you have a sparse graph, that means your connections are lesser. The ratio is smaller, right? So in dense graph, your two-layer GNN is very good. I mean, it would just consider most of the neighbors. So you have to be careful. So I cannot say that you go with 2 or 3 or 1, but for decent size of graph, in 1 or 2 works really fine. 3 you can use if you have very large, very big graph, right? I mean, you should try all of these things. If you are really interested, just go back. You have all the code in PyTorch available online. Yes, PyTorch geometric is there, where you have GCN layers. You can just directly apply, just run, do some experiments. You can also construct your own random graph from NetworkX library. There is something called NetworkX library in Python. Yes, so you can create your own random graph also. Right? So play with this, you will find it interesting that how the things are changing. Okay, so we have less time, I think. Okay, I have half an hour, it's 3:30. Yeah, so I think I won't go into the detail of 3D. The graph part is done, right? I have told you the graph learning, graph applications, how the input would be, what's the aim, right? What's the model look like, message passing and so on, and what's the problem. Over smoothing is one problem, the other problem is the scalability. The problem with scalability is you represent your graph with adjacency matrix whose size is n cross n, where n is your number of nodes. It increases by a lot when your graph becomes bigger. Even if it's a sparse graph, there are so many zeros. With dense graph, there would be so many ones. With sparse graph, there would be so many zeros, but your matrix size would be the same. So you are having memory issues, right? So what you do is, I mean, scalability, there are some papers which work on scalability of GNNs where they try to make it faster. And so one thing that came when I was working on this was a sparse matrix usage in PyTorch. That is one thing that you can use, because sparse matrix version of PyTorch was not there before. Now if you use it, what is the meaning of sparse matrix representation? What is the other representation of graph other than adjacency matrix? Edge list. Edge list is the sparse matrix operation that is there in the PyTorch, where you store only the edges which are present and not the zeros, right? So that is another problem that is there. Okay, there are other set of papers which work on scalability. Okay, so the graph part is done. I also work on 3D. Won't be covering too much in detail, but I'll give you some idea, right? So applications of 3D data, so many. I mean, I think this is the most common that you all would be knowing, autonomous driving, and also maybe AR, VR, right? In robotics also is there anyway that there are these robots and drones and all, but they also work with 3D scenes and so on. So there are many applications in all of these areas, even medical image processing, where they work with 3D models of some bio stuff, where let's say for surgery or for some clinical operation if they want to study, for education purposes also they do, right? So some applications of 3D data. Now the idea is, what are the representation? I have told you about the graph representation. Now how do you represent a 3D data? Image you know, text you know, graph you know now. How do you use 3D data in your, let's say, network, right? Or how do you process 3D data? So if you ask me what is the easiest way? The easiest way is, can I say that I have a 3D model, I take multiple images of this 3D model and I apply a simple CNN? Because then there is no headache of constructing a new CNN for 3D data. You can just simply use image CNN, right? So this was the first set of papers that came on multi-view in this area. Multi-view based papers came initially, where they were projecting this 3D model into 2D and getting multiple images of that model so that they cover all the angles, right? And just apply simple CNN, right? Then people said, can we not use, because it's an irregular data, right? 3D is like an irregular data. So people said, can we not make our own convolution operation for 3D? But you need what for that? You need a grid. For CNN application, applying filters, you need 3D grid. So you had 2D grid already in images. Now can we extend this 3D, the convolution to 3D grid just by adding a one dimension? So this is volumetric representation, where what they did was, you have a 3D model, you put a box over that like a cube, right? And now you cut this cube into different cells. Now can you say that this cell is a pixel in image? Right? But it's a 3D pixel. Now you apply 3D CNN. The filter size is just one dimension extra. So that is a volumetric representation which people used.
DeepMind did something similar recently. They had a single cubic millimeter of the human tissue, human brain tissue. So they cut it into 5,000 or 5,000 parts.
Okay.
Used segmentation learning, and I think then they mapped it into a 3D brain. They
Okay.
recently did that.
Okay. Yeah, I haven't seen that, but yeah, that's interesting. Actually, this volumetric is quite old by now, but maybe they might be using it for this brain thing, which is new.
Mapping the brain.
Yeah, so the solution, the way they are doing might be an older one, but they are using it for new applications. So yeah. Yeah, text to 3D is like new, this Gen AI and all, which is, yeah, but this is a deeper understanding of 3D. I mean, that's also there, but this is more like how do you use these. So for some, if you create your own model, you will use one of these inputs. So I am mostly mentioning that what are the inputs that, or what kind of representation you want to use for 3D, or what are good. If you work with these, you will get to know what are the drawbacks with which one. So volumetric has its own drawbacks. Multi-view has its own, that it would not capture it, just capturing images, but would not capture the geometry, right? So it might be great for simple classification, but not for some other task. Volumetric has its own problem, right? The problem for volumetric is what? Because it is a 3D grid, so n cross n cross n matrix size of zeros and ones. Because when you have a 3D model, you fit a grid, you say that wherever, in which cell some model part is there, you make that cell as 1. So there are filled and empty cells in volumetric. So many are zeros also. So computationally expensive. Then here comes point cloud after volumetric. Point cloud was popular because they say that you don't need any grid. Can you apply directly some convolution, I mean directly to point cloud, no grid, nothing. Because point clouds are unordered, there is no grid. So the idea is we need a model which is permutationally invariant. Why are we doing grid? Because so that our location is fixed, there is no issue of permutation invariance. But then there comes some model where they say that there is no issue, we can directly apply to point clouds. And those models are permutationally invariant. Then mesh is a different set because mesh also comes in computer graphics. But then people started also applying in deep learning where you say that instead of point cloud, can you make a mesh? So mesh is nothing but putting a surface on point cloud. I'll see if I can cover some, at least just to explain what is a mesh. Okay, so before deep learning, this multi-view geometry is an area where people used to get 3D reconstruction of these models. So how do we see 3D world? We cannot see 3D world with one eye. We need multi-view, right, geometry. That's why we can see the depth, right? So this area was very popular. This is like non-deep learning area where they say that from 2 views, if you take picture of the same thing from 2 views, you can reconstruct its 3D version. Yeah, Nerf is a new one, but this is an old one. Yeah, Nerf is also similar, where you have multiple views. Okay, the challenges are same, which I've already mentioned, right? Irregular, unordered, unstructured, and so on. And we are saying that CNNs are great for images, they are not suitable for point clouds. How can you apply? So the another problem was this, at least now maybe it might not be there because now people have self-supervised, few short learning methods. But when I started working on that, the idea was for 3D data, you need a lot of data for good training. Very, very heavy data that you need, then only it would perform well. So that was also again a problem, and when you are doing classification, you need labeled data. So that was also again the problem. So then other papers started coming with self-supervised, few shot and so on, but a lot of literature. These are some of the tasks that we perform with 3D. Shape classification, which is usually done with a single object. Let's say this is a lamp, this is a chair, car, table, and so on. This is shape retrieval, where you say that I have this chair, and I have a database of 3D. Can I retrieve similar models? This is key point detection, where you have important landmark points. For example, let's say for a human body, these joints are landmark points where there is a movement. So these are important points, right? On face, maybe eyes, nose, mouth, ear, these are important points. So some landmark points. So these are some things, and then there is this something called shape correspondence. Similar to I have shown image correspondence, matching of two house points, right? Shape correspondence, like here they are matching one edge to the other edge of the chair on the top right, right? So can you find out which leg of the chair belongs to which the leg of the other chair? So where can this be useful? We'll see, in the next slide. Shape correspondence is also a very important task. Then semantic segmentation, where in the scene, if you see, ceiling is labeled with the green color, neon green kind of color, and then you have all the chairs with red, you have tables with violet, and maybe the floor with blue. You also have object detection, which is very useful in autonomous driving. Very popular there. Object detection, the car is moving, it would just take the 3D LiDAR data, right? And then from the LiDAR data, LiDAR is a sensor basically, and then it collects the 3D data in point cloud version. And then can you detect where are the cars, objects, and so on. You also have normal estimation, which is more like understanding the surface of point cloud. When you have point cloud, let's say you make a tangent vector over that point, and then you take a perpendicular vector over your tangent, which is your normal vector. So normal vector is actually, it would tell you the orientation of point, right? So these are some of the properties and tasks also. These are some more tasks. Tracking is again, object detection and tracking are from autonomous driving, that where would the next car be moving in the next frame. The top right is a pose estimation, where that is for a video, that one. And if you see, they are actually making a skeleton in a 3D grid kind of a box. So you first detect the joints of the person in a video, and then you track its movement, and then you say that what is the action that it is doing. It is called as activity recognition. The application or problem is called as activity recognition. Are you playing, are you running? So it says playing, running, something like that. Okay, the other one is a pose transfer. It is very useful in animation transfer. So here actually the shape correspondence one that I was mentioning is very useful here. So pose transfer, animation transfer, all of you I think understand that if I am dancing and I want to move my dance moves to some other animated character, how do I do that? So movies and all, how do they make it? So this is very useful. This is also in 3D. Okay, there is a very much difficulty in pose transfer because there are different scenarios. There are people with 2 legs, there are people with 4 legs. People means animals with 4 legs, right? Can you transfer 2-leg person activity to a 4-leg? So usually we call it as biped and quadruped. So can you transfer poses between biped and quadruped or quadruped and biped? That's very challenging. People are still doing quad to quad or bi to bi. So very challenging problem this is, and also very popular, many papers. Some new applications, mostly from Gen AI, which everyone is fascinated about. Some scene synthesis, can you generate new scenes? Can you, if I just say that from text instruction, okay, I want a swimming pool in this scene. So I would do something and then generate a swimming pool there, right? There. Uh, if a scene is not complete, then can you complete it? Especially, let's say, for interior designing and all, these softwares can be useful. I mean, if you make a software out of it. Scene understanding, where you do, let's say, a segmentation of that, and maybe, let's say, you do something else after that. So segmentation, where there is a bed and other things, paintings. Also scan completion. Scan completion is mostly where when you have some sensor, you collect your data with some sensor. Let's say a 3D LiDAR, right? Those data that you collect are not always good. They are very incomplete or noisy. So if you see this data, there is a very incomplete, holes and all, right? So can you complete it and make it a bit smoother? So this is another task. Activity recognition I have already mentioned, which was in videos with skeleton. Now this person is doing activity recognition in complete 3D without skeleton. So there are different versions of 3D models, human models. One is a skeleton. The another one is called as a very new term called SMPL. You can look at that. SMPL body parameters, where you don't work with skeleton, you work with a full body. So it's more like, okay, move in the scene and open the fridge, or let's say sit on the chair. It's a very, very difficult problem, because you need to find out where is the empty space in the scene where the human would move. Human would not know. You want to make the machine learn. So the human wants to move to the scene, but then it should not intersect with any object, right? And then if it is opening, if it is also doing some action, which is actually a very tough job, you're also changing the object geometry, right? So only human is not moving, then your object part is also moving. So very challenging problem. One of my students is also working on this. And then robot navigation, let's say robot is moving in some indoor scenes, and can you give some text instruction that, okay, where is this thing in the room, and so on, right? So these are very interesting tasks. And there are some, okay, these tasks I have already mentioned, I think. Object classification, part segmentation looks something like this, where semantically similar things are of the same color. And let's say, for example, earbuds of the headphone. So earbuds of the headphone are semantically similar, right? So you want them to be closer in the feature space, those points. So those are with the yellow color, whereas headband is of the different color, right? So that's there. Semantic segmentation, I've already mentioned that all the cars are with the same color, trees are with the same color there. So you want to segment all the objects there. These are some of the data sets which I took from some survey paper. This table has lot of data sets with many, many tasks, autonomous driving tasks, robotics, classification, right? Tracking, detection, many other. These are some popular data sets that we work with mostly for the tasks which are mentioned in the parenthesis, right? Okay, I think I'll skip these. So basically my idea was to mention that there were 4 representations that I mentioned: multi-view, volumetric, point cloud, and then mesh. So these were the flow that initially multi-view papers came, and then they said that, okay, what is the problem with that? So volumetric came, which was saying that can we use 3D CNN instead of 2D CNN. And then volumetric had some problems, so point-based method, which is a point net, which is a very popular method, this came, which was saying that there is no problem if you directly apply convolution operation to point cloud, which is permutationally invariant. Then there are more graph-based methods also came, where they say that in a point cloud you construct a KNN graph and you apply message passing. Can it do better? Then mesh-based method is anyway a bit different because this is also from computer graphics, but this mesh CNN also started curating a new convolution operation specifically for meshes. So there are many methods where the convolution operation is not just single, it depends on the data. Many papers which work on different sets of data. Yeah, I think I'm going to skip these slides. It is the same thing that I've told you the story that multiview, initially multiview came, then they say that can we directly do 3D convolution. Then this is volumetric based approach where we are fitting the bunny into the unit or any cube size. These are the volumetric based approaches. I think I'm not going deeper into this. Problems with voxelization, I mean volumetric is something. Let's not talk about that. Then point cloud method based methods came, which are like PointNet and PointNet++ from CVPR and NeurIPS, and this is actually the point cloud architecture, I'll tell you. Yeah, so I have missed a lot of details, but yeah, that's okay, I think. So if you see this network, you have input which is n cross 3. N cross 3 I mentioned, right? It's a point cloud for one point cloud, but there are many such point clouds, right? You have n cross 3. You do some input transform, which is similar to, let's say, normalization or something, so that everything is aligned. And then they are using simple MLPs. It works out. Feature transform similar to input transform, and then MLPs, and then max pooling similar to that. Very simple architecture. And then finally you do softmax and then classification. So this was a very good paper. I mean, when it came, it became so popular that people are still using it as encoder or some form. These are some results from that paper. Part segmentation. If you see, the data set is very difficult. If you see here the left side part of the data, incomplete data. There are some holes, noise, right? So it's not very easy to work with such data. These are semantic segmentation, a bit harder than single object. This is a single object data set, but this is a scene data set. So scene data sets are more complex, right? So semantic segmentations. And then there are some limitations of PointNet because they were using some simple MLPs in a max pooling. So they were saying that they are good if you have to retain a global shape. If you just want to learn some global shape, that there is a chair, there is some object, but they are maybe not considering some local information around each point. This was the claim. So although PointNet does okay, but it was the case that they don't capture local information, they just focus on global information because you have seen the architecture. So then the PointNet++ came. PointNet++ is similar to PointNet. The only problem is they do some kind of hierarchical feature learning. And hierarchical means they take a point in every point cloud and they take a neighborhood, a ball around. Ball means you can say a ball with epsilon radius, right? Now you say that if a point is a very dense region, is at the dense region, that means the neighborhood is very rich. And if it is at the sparse region, it's less number of neighbors. So these kind of local geometries are being captured here. So they are saying that, let's say this is a point cloud, and they take point and the neighbor. After, with these kind of point and neighbors, they aggregate things and then they sample those points. So basically, you are reducing the original size of point cloud to a smaller size by considering some neighborhood local information. And then you again do the same thing. So your point cloud would finally be reduced to, let's say, 1 point or something. If you want to do classification, you can just do, you get the embedding vector. You can just apply softmax and use the classification scores there, right? They are actually, so this is the classification that they are doing. But they are interpolating and coming back to the original size for segmentation. So you need actually the same size input for segmentation by, if you remember, I have mentioned that if you want to classify whether this is a point cloud of a table or a chair, you just need one vector for that whole thing, right? For a whole point cloud, after few layers, you need one vector for the whole point cloud so that you can apply softmax and get the score. But for segmentation, you need label for each point. If you remember this, You need label for each point because that's how you color it in the end, right? So mathematically, you need one label for one point cloud, but you need one label for one point in the point cloud in segmentation. So that means you need the original size of point cloud to actually do the prediction. So that's why they converted the point cloud to the same size point cloud and then do segmentation. So it's nothing but basically matching the dimension so that nothing goes wrong. Yeah, almost coming to an end. I have a couple of slides. So this is a slide which has mostly nothing. So the idea is many methods started working on supervised methods, like normal supervised method that you have started working with. But nowadays, people are moving to unsupervised, self-supervised, few short learning, and so on. So there are many papers that are not, let's say, using labels, or very few percentage of labels they are using. They are moving towards self-supervision mostly, what I have seen, so that you don't need annotation or something. Especially, I've seen this in autonomous driving thing also, object detection and tracking. So this is also one figure from some paper, survey paper, where some methods are mentioned from multi-view representation. So multi-view network in blue, then volumetric network in gray, then point-based methods in some other color, I think violet or other blue, then graph-based methods, and so on. So different kinds of method which are using different input for 3D. And this is a very popular GitHub repo for point cloud papers. This started in 2017, and then they always have some latest papers from top conferences and links also, link to the paper, and if there is a link to the code, they also mention the link to the code. You can also find 3D data sets on this link. So I think the similar repositories are also there now for graphs and all, so you can always find out, right? Okay, thank you.